Let's start with a review of strategies in an extensive form game, since understanding strategy is crucial for the rest of the course. Consider the extensive form game shown on the slide. In this game, player 1 has 32 strategies. That is, player 1 has 5 information sets where player 1 chooses an action from a set of 2 potential actions. And so he has 2 to the power of 5 strategies, which is 32 possible combinations of actions. Now, we derive subgame perfect equilibria of this game by backward induction. We derive the best response of player 1 at each terminal node first, which is indicated by the orange lines. Given these best responses of player 1, the player 2 now decides what to do at each of her information sets. The best responses of player 2 are given by the orange lines. Finally, the player 1 decides what to do given the best response of player 2 and the best responses of player 1 at the terminal nodes. This completes the derivation of subgame perfect equilibrium, and the subgame perfect equilibrium is given by the pair of strategies shown here. A note here that player 1 has 31 ways he can deviate from the subgame perfect equilibrium strategy. This means that we need to check 31 deviations to check if the obtained subgame perfect equilibrium strategy is indeed a subgame perfect equilibrium. And this is very cumbersome. It turns out that we do not need to check all 31 deviations to check the validity of subgame perfect equilibrium strategy we derived due to what is called one-shot deviation principle. One-shot deviation principle says that we only need to check one deviation at each information set to see if any given strategy is a subgame perfect equilibrium. That is, we fix a strategy at all other information sets and consider deviation at only one information set at a time. For the example we are considering here, this means that we only need to check 6 deviations. And furthermore, we have already checked that these deviations cannot be profitable by backward induction. We now introduce the concept of discounting in dynamic games. To see what discounting is, consider receiving 10,000 yen today versus 10,000 yen in 1 year. 10,000 yen today may be worth more because you could be simply dead in a year. Alternatively, you could think that 10,000 yen today could make some interest by lending today and get it back in a year with earned interest. All these suggest that the value of 10,000 yen today is worth more today than in a year from now. To capture this idea, we introduce something called discount factor delta, which is the ratio given by the value of something in the next period over the value of the same object today. Since the numerator is smaller than the denominator if the future is discounted, we assume that the discount factor is smaller than 1. What is the implication of discount factor in terms of players' payoffs in dynamic games? It implies that the payoff received in 1 period from now is discounted by delta, and the payoff received in 2 periods from now is discounted by delta squared and so on. Therefore, the payoff received in t periods from now is discounted by delta to the power of t. In general, we can write down the total discounted payoff of a player who receives a temporary payoff of UK in period K can be written as the sum of all discounted temporary payoffs. Now, let's see how the discount factor plays a role in the context of alternative bargaining model. Consider the following two-period alternative bargaining game where players take turns to play ultimatum game. In the first period, player 1 offers a division of payoffs where player 1 gets x1 and player 2 gets b minus x1. And then player 2 decides to accept or reject the offer. If player 2 accepts the offer, then the game ends. But if player 2 rejects the offer, then player 2 gets to offer division of payoffs in the second period. In the second period, player 2 offers a division of payoffs where player 1 gets x2 and player 2 gets b minus x2. Then player 1 decides to accept or reject the offer. If player 1 rejects the offer, both players. Let us now consider another type of dynamic game called stackable game. Here, the game proceeds in the following way. First, farm 1 chooses its output level or quantity x1 with a total production cost of C times x1, where C is a positive constant. Second, farm 2 observes x1 and chooses its output level x2 with a total production cost of C times x2. Lastly, the market price P, which is a function of the aggregate output, is determined by the linear inverse demand function given by A minus B times the aggregate output. Here, A is the intercept parameter and B is the slope parameter. Farm I's profit is given by the total revenue minus the total cost, where the total revenue is simply the product of price and output xi. Note here that we have already plugged inverse demand function into the price, which allows us to express every component of the profit function in terms of the output. Note here that we cannot write down the game tree in a precise way because there are infinitely many information sets here, but you can get the idea from the graph on the slide. We solve this game by backward induction as usual, and start with farm 2's problem that pins down the best response of farm 2 for each possible output of farm 1. Taking the first order condition of farm 2's profit with respect to x2 for a given level of x1 gives the best response of farm 2 for each possible value of output x1. Now, taking the best response function of farm 2 as given, farm 1 maximizes its own profit. Note here that farm 1's problem is different from farm 2's problem since farm 1 takes into account the fact that farm 2 changes its output x2 depending on x1, while farm 2 takes x1 as given. Solving the problem of farm 1 gives subgame perfect equilibrium output level x1 star. Therefore, the subgame perfect equilibrium is x1 star and x2 star shown on the slide. Note that subgame perfect equilibrium is a strategy profile that describes all the contingent plan of actions, and so player 2's strategy has to be a function of x1. You should not provide the output level of farm 2 as the subgame perfect equilibrium.